All right, everyone, welcome to session 4B for SAZERAC. We'll have our first talk by Brian Welch. Brian, would you like to share your screen?
Yep, here it goes.
Thank you. And Brian will be talking to us about RELICS Parsec-scale star clusters observed in the first billion years.
All right, thank you. Yep, I'm Brian Welch. I am a PhD student at Johns Hopkins, and I'm going to be talking about some superlative lensed galaxies that we found in the RELICS survey, including one that is magnified enough to see parsec-scale star clusters at redshift greater than 6. So first, a little background on RELICS. RELICS was a 188 orbit Hubble program that was targeting 41 massive galaxy clusters with the goal of looking for some of the best and brightest high redshift lensed galaxies that we could find. So by looking at a wide area, the goal was to be able to pick out sort of the most interesting objects that we could find with Hubble. We also had over 1,000 hours of Spitzer, which really helps with some of these higher redshift galaxies to make sure that we know that they are real high redshift galaxies as opposed to lower redshift interlopers. I'll talk a little bit more about that in a bit. But first, just quickly, why we like gravitational lensing for some of these studies. The big reason is that it magnifies these distant galaxies and gives us much better spatial resolution than we could hope for with current or even next generation space telescopes. So this is a lensed galaxy at redshift about 2.5. And you can see the source reconstruction here has all these small clumps of stars that are on scales of a few tens of parsecs each. And then when you take this back to HST or even JwSt resolution, you lose a lot of that information. You lose a lot of these little details. So if we really want to study how these galaxies are forming, we really need lensing to give us this resolution boost so that we can see down to scales similar to what we can see in local galaxies to study star formation across the board in some of these objects. I also just quickly want to show this slide from Dan Koh's talk earlier this week, just comparing the sizes to scale of some of these lensed galaxies that we're going to be looking at. Besides these two that hopefully you can see my mouse here, which do not have James Webb time, all of these are going to be targets of James Webb observations. But what I wanted to point out here is just sort of a size comparison of some of these galaxies. So for example, this is the longest lensed arc at redshift 6 that I'm going to be talking about in detail in this talk. And you can see on this slide already just how much larger this appears than some of these smaller, more point source like redshift 6 galaxies. And just how much more resolution we're going to be able to get, spatial resolution we can get with these lensed objects. So to jump into this one in particular, this is a 15 arc second long lensed arc that we've named the Sunrise arc. It is the most highly magnified galaxy at a redshift of 6. Overall, this galaxy is magnified by about a factor of 300. So you can see in this figure on the right, this red line here is the lensing critical curve. It crosses the arc twice, so we're seeing a total of 3 multiple images of this galaxy. And especially in this middle segment here, the critical curve runs almost parallel to the arc image that we see. So we're really getting really high magnifications across the board here, giving us a lot of great details into this galaxy structure. So to actually get at all of the substructure that we see in this galaxy, I've been using a forward model technique where I create a model of the galaxy in the source plane, and then run that through our lens model to create this image plane reconstruction that you see on the left. And with this, we're able to identify a total of 7 individual star-forming clumps that really span the breadth of this galaxy. So you can see clumps 3 and 4 here form sort of a tight core at the center of this galaxy. And then we have our clump labeled clump number 1 all the way out to almost 500 parsecs from the center. And the radius of this galaxy is about 200 parsecs. So we're really seeing, the entire width of the galaxy from the very center all the way out to the edges. And this is going to help us in the future with determining, how this galaxy really formed once we get some spectroscopic data, which I'm going to talk about a little bit at the end. But this is really going to help us to figure out, if this galaxy is sort of accreting more star-forming clumps from outside, or if it's forming most of its stars from the center or inside out. So this is going to be a great opportunity to study this in the future with James Webb, to get a sense of how this is really coming together. The other interesting Redshift 6 galaxy that I want to highlight here is this one. This is the Brightest Redshift 6 lensed galaxy. So its AB magnitude is about 23. It's magnified by a factor of about 20. So this just seems like a particularly interesting sort of extreme case, where obviously this one clump here is significantly brighter than anything else we've seen. So it's a very interesting object to keep looking at. So just to compare these to some other lensed clumps, I just want to point out here, this is the clump number 1 from the Sunrise arc, which is the one we have the best radius constraint on so far. The radius is less than 6 parsecs here. It's still unresolved in HST, so we can only set that upper limit, but it's already the smallest lensed clump at Redshift 6 that we found. And it's getting down to scales that, we previously could only really look at lower redshifts, and even scales that we could look at in the Milky Way and other local galaxies. So now we're able to do that at much higher redshift, which is very exciting, and very exciting to continue following up. And then also the bright clump that I just showed on the previous slide is obviously significantly brighter than anything else of similar size. So it seems like a pretty extreme object. We don't have too many details about it right now, but it seems like it might be going through some sort of burst of star formation. So it's going to be, again, a very interesting object to follow up with James Webb in the future. The last arc that I want to highlight here is this lensed arc at Redshift 10. This is one that Victoria Straight mentioned in her talk yesterday as well. She's done great work with Spitzer to really pin down the redshift of this and kind of break the degeneracy with a lower redshift SED. So this is a very solid Redshift 10 galaxy at this point. And again, this one is, it's the only lensed arc at Redshift 10, so it gives us the best spatial resolution of any galaxy at this high of a redshift. So we can put our forward model to use here again. And you can see in this plot, I'm showing the actual HST data on the left side, and then the right is our forward model reconstruction. And what really shines out here is that we have 3 substructures within this galaxy. So 3 clumps that we can study. These are all pretty preliminary fits, but this is something that I am continuing to work on. And if we add these to that plot I showed earlier, you can see the radii that we get for each of these are just below 100 parsecs. And one interesting thing is that these seem to be brighter than similar sized clumps at lower redshift, implying a potentially increased star formation rate for an object of similar size, so higher star formation rate density, which is something, again, that we're going to want to follow up spectroscopically with James Webb. So this is another great target to continue looking at in the future. So I just want to end here with our vision for the future. We have one program for these galaxies that's been accepted for James Webb Cycle 1, and that's on the Sunrise arc. So we're going to be getting near-cam imaging to hopefully resolve all of these clumps and set not just upper limits, but get actual radius measurements for all of these. And then the other thing that I'm very excited about is we're going to use the near-spec MSA to put slits on each of these clumps. So we're going to be able to get spectra, which will give us solid star formation rates. It'll give us metallicities. And like I was saying before, it'll give us these things across the width of the galaxy. So we can see, if there are any metallicity gradients across this galaxy. We can see where the higher star formation rates are and really sort of deconstruct, how this galaxy seems to be forming and what's going on there at this galaxy in the epoch of reionization. So I'll leave you with that. It's a very exciting time. I'm very excited for James Webb and to get my hands on some of this data. So I'll stop there and take any questions.
All right, thank you so much, Brian. Give it just a little bit of time for people to type any questions they have in the Slack under session 4B.
Okay, how did you determine the redshift of the sunrise arc?
So right now it's just photometrically. So let's see if I can go back to a previous slide here. So it's just photometrically. We do an SED fit to the HST data. And the best fit that we get is redshift of about 6.2. Since we have this steep drop off here below the Lyman break, it's a solid redshift 6 galaxy, but we don't have a spec Z for it yet.
Next question, how much of the upper limit for the sunrise arc clump 1 of less than 6 parsecs can be changed by the uncertainties from the math model and the redshift?
So the redshift, photometrically, we're pretty solid on that. So that we don't expect to change too much. The mass model is a little bit more uncertain. So this cluster really only has a few multiple images that we can use to pin down the reconstruction, the lens model reconstruction. So I don't have an exact number, but I would say, maybe a factor of a couple. I think we have a couple different lens models, and the largest sizes are maybe slightly more than 10 parsecs, but I would have to double check those exact numbers. But yes, the mass model is a little bit uncertain right now. And this is something that we are, again, hoping to get pinned down a little bit more with our web data if we can get a few more multiple images.
Okay, great. There's a question about whether you've considered ALMA observations of this sort.
We have. So we actually considered putting in an ALMA proposal for the last cycle, but we decided to hold off since we are going for James Webb. We're hoping that Webb will give us the spec Z for this, so then we can sort of optimize our ALMA observations a little bit more, as opposed to scanning across to try to get what the redshift is. So the plan is once we have a spec Z, we will target this with ALMA and try to get a lot more spectroscopic information there.
Great. All right. Well, thank you. And if there are any other questions, please type them in Slack, and Brian can check that later. Our next talk will be by Anton Bakaeus. Would you like to share your screen, Anton?
Yep. So, right. I'm ready to begin, so I can start?
Yeah, go ahead.
All right. So, hi, my name is Anton Bakaeus. I'm a PhD student working at Uppsala University. For the ones that don't recognize me or so on. I work with Erik Zachrisson and Martin Salén as supervisors. So I will continue now to present some work on a paper that's coming up quite soon when we're looking at the conditions detecting lens top 3 galaxies in blind surveys with JwSt, RST, and Euclid, the ones that we applied it to. So is the paper with some collaborators. We also have Daniel Scherer, Eli Visbal, and a student, Emma Fransson, working with us, and Sanjita Malhotra, James Rhodes, Martin Salén. So thank you. I will pay tribute to those for their contribution. Right. So when we're looking for the first generation of stars or galaxies in the universe, so we wanted to be able to detect them. And to begin with, just some background here, if we're looking to detect top 3 stars, for example, you know, as you all know, they form in mini halos at quite high redshifts, forming already at redshifts of 30 or so, that regime. So typically yields only quite low stellar masses. So there, if you're assuming a certain star formation efficiency here, fraction of baryons forming stars, you only have like 30 to 100 or so approximately worth of total stellar mass. So are they detectable? Well, that's quite unlikely. Even with very strong gravitational lensing due to their low brightness and their high redshift and their quite short signals, small systems. I should mention also, well, maybe there are circumstances where we can detect top 3 stars forming in some pockets of pristine gas that may remain pristine to lower redshifts. That's possible. These kind of cluster lenses, for example, that Brian just talked about in the previous presentation, we can get really large magnifications and maybe detect some of these really low metallicity stars or clusters of stars. So the top 3 galaxies that we've been considering or focusing on rather form in the atomic cooling halos, where you have atomic line emission cooling at redshifts of about 15 or so. The typical masses we're considering then are quite different. So they're at redshift 10, it may reach something like thousands or tens of thousands solar masses with a given star formation efficiency. So the kind of objects that we're looking for, I should also mention that we're put quite stringent requirements to these, because we're looking at pristine objects in the kind of the work that we're doing. So we're not looking at objects that had formed a significant amount of metals and which will pollute the signal and so on. But we rather try to stick to those ones that had really pristine signals. So that requires delayed star formation in the mini halos that makes up the substance for the bigger halo. So you have some mechanisms: Lyman-Werner radiation, dissociating H2, baryonic spinning motion, and ionized feedback, and that may suppress star formation, so that these atomic cooling halos may remain pristine to quite low redshifts, at which we hope we can detect the pristine signal. So are these detectable? Well, with gravitational lensing, they certainly are, as I will try to argue here in the coming slides. So the gravitational lensing that we apply adds a probabilistic aspect of the detection of these objects. So we apply gravitational lensing to randomly oriented sky surveys. So as opposed to targeting specific cluster lenses, for example, where you have very high magnifications, we did our calculations on random surveys rather, in which you can formulate a function here that tells you the magnification probability, or the probability of attaining a certain magnification, and that has the kind of scaling as you see here as an inverse square, more or less in the relevant range where we're looking to detect top 3 galaxies. So when we're trying to detect an object, we want to have a certain magnification which will lift the object above the detection threshold of a particular telescope. So that's what we apply, and this places a minimum requirement on the co-moving number density of these top 3 galaxies, and these are the ones that we calculate and then compare to simulations to see whether the amount of objects are enough, the co-moving number density is enough to get a sufficient amount of them appearing in surveys in the future. So the kind of results that we got, I'll bring your attention first to the equation just to tell you so that you're understanding what figures comes from here. But what we do is we calculate the minimum co-moving number density. This is produced from the magnification probability function, where you're looking at the magnification which will bring it above the detection threshold of any given telescope. The co-moving survey volume, so that depends on the survey area of the telescope, so how wide it will survey, of course. And it also has a dependency on the cosmic time span in that volume and how that relates to the lifetime of the signature if we're looking at truly pristine signal. So that goes into this as well. So the results here on the left, if we begin there, we have look for the helium, ionized helium 1640 emission line coming from, that's argued a very specific line for us, POC3 galaxies, and when we're looking to observe them. So what you can bring with you here from the figure is that this looks, you can see them as kind of exclusion plots. So the simulations, which predict the number density of a certain POC3 galaxy of a certain mass, ends up in the regime that you see here, more or less. We have the Inayoshi simulations down that's quite below here, and we can consider that as like lower estimates, but the ones on the top here maybe be reasonable estimates on the abundance of these objects. So they fall below the lines of the different telescopes here. So that means that we are define that as an undetectable regime. So unfortunately, spectroscopy on the helium emission line, ionized helium emission line, seems to be unprobable to detect these kind of objects in the surface from applying our method to it. On the other hand, using photometry on the 1500 angstrom continuum in order to detect them, it seems as is another story, because in this scenario, several of the telescopes seems to predict that we would find them with photometry when we're applying our randomly oriented sky surveys here. So RST seems to be performing the best. Euclid also seems to perform quite well. So you can see here that the large survey area of telescopes like RST seems to be very fortunate very good for detecting them photometry, while on the other hand, in spectroscopy, there seems to be a quite even game. But we also have restrictions on the maximum allowed magnification before we get differential lensing and these kind of problems that will compromise or make make it harder to understand what we're seeing, and we need to develop our models further for that kind of high magnifications. Yeah. So furthermore, looking at looking at a wider redshift range, we looked at these kind of model predictions here. We have different star formation efficiencies. So at the redshift 10, some of the predictions here, the Stiavelli case, the one that performs best here, it comes really close at redshift 10, but that's only for a very high star formation efficiency, which might be quite unreasonably high. So we're rather considering realistic numbers to be around this line here, the red line, for example, here, or some of these lines up here above. So you can see that they're all over across this redshift range that we're looking at. It seems that we have some problems with the number densities falling quite short. And this is also for JwSt with helium, spectroscopy on the helium emission line here I mentioned previously. So the best area seems to be around redshift 10 or so, but also maybe at lower redshifts, there could be also reasons to believe that we could actually find them, but we haven't investigated the lower redshift range yet. So conclusions, we will likely detect, with our models, we predict that we will likely detect POC3 galaxies, pristine ones, photometrically, at least in the 1500 angstrom continuum. We will not be able to spectroscopically confirm that we have detected POC3 galaxies. It seems, with our models at least, that they're based on the ionized helium 1640 emission line being one of the good indicators for POC3. It seems to say that the number densities are a bit too low to expect this. And some community homework I thought would be appropriate. So whether or not can maybe hydro simulations allow more massive POC3 galaxies to form, so higher star formation efficiency without sacrificing number density. So we have some requirements here. I won't go into that, but it seems if we can place the number densities at these kind of values, so a couple of thousand per cubic megaparsecs for a couple of thousand solar mass galaxies, that would do the trick. Yeah, so these are just some numbers here, and furthermore, like I just mentioned, the evolution of this at low redshift. So these kind of lines here would pan out at lower redshifts and level off at some point, and maybe simulations then at lower redshift could kind of converge on this, but we're not sure of that. Of course, when we're looking at that's increasingly being a lot of work done on that. So maybe that will find find out more about that in the future here. So with that, I would like to just thank you for listening and going. Yeah.
All right, thank you, Anton. Give a minute for people to write any questions in the Slack. We'll just wait a few seconds for people to have time to write questions.
Yeah.
So what fraction of redshift 10 galaxies are population 3 dominated according to the simulation predictions you used?
What fraction in the simulation? So the prediction that we used and the Visbal simulations, because he's one of the co-authors here, he's simulating them as pristine objects there. So I guess that would be all of them in that case, because that's been applied to just having no prior star formation, really. So that would be catching them quite early when they start to form stars. In the other simulations, we're just using the fact that they're predicting, for example, Stiavelli is predicting the number density of atomic cooling halos, and then we translate that into a mass. So in that case, it could be a wider range of whether or not there would be POP3 bright or not. It's fine. So.
The next question is, why is the N-min value flat above a certain stellar mass range?
So I guess that would be the kind of figures that I took. I'm just taking them here. Yeah, these kind of flat areas here. So these are the areas where the telescopes do not need any gravitational lensing at all. So they're, for the higher masses, you can see that the JwSt is reaching quite deep here without the need for magnification. So when you're starting to bend upwards, that's when magnification kicks in. And the same thing here, you see also that they're positioned at different heights here, at different places on the y-axis, and that's the different survey area of the different telescopes. So I guess that was the question, right? I hope.
See if any other questions pop up here.
Do your simulations show how the heavier elements are synthesized?
How the hell heavier elements? So not really. I wouldn't want to say too much about that. I haven't been involved that much in the simulation work. That's the work by, for example, Visbal, that's a co-author. So I think that I would have to ask him more about how that works out and how you actually go over to the when you're saying that you're in a POP2 population, you're transitioning over. But that's definitely well defined when you're transitioning from pristine to metal enriched. Yeah, but what I could mention is that we're putting a certain lifetime on our object. So if we say that it begins to form stars, we won't wait longer than 10 million years before we're supposed to extract the spectrum. If we're looking at 10 million years after star formation is commenced, then we're considering the POP3 signature to be removed, and we would rather see an enriched galaxy.
All right, thank you, Anton. If anybody has any more questions, please put them in the Slack. But with that, we'll move on to our next speaker, who is Mauro Stepanon. Would you like to share your screen, Mauro? Yep. Mauro's talk is on the star formation efficiency in the first billion years of cosmic size.
Okay. Hello, everybody. I'm Mauro Stepanon. I'm a postdoc in Leiden. And before actually starting, I would like to acknowledge my main collaborator that you see listed below here in this slide. in the recent years, an increasing number of works have suggested the existence of very massive galaxies in the early universe. And these massive galaxies are raising questions about how efficiently mass could have assembled in the early universe. And one way to approach this problem could be to compare the evolution of the accretion of dark matter halo to the assembly of stellar mass. But if we want to constrain robustly, in a robust way, the stellar mass, we need access to the rest frame optical light. And at high redshift, the rest frame optical gets shifted to the near infrared or even mid infrared. And we have seen on Monday and also in the following days that JwSt is going to provide a exciting amount of data which will be useful to assess this kind of problems. But for the meantime, we can also use the legacy from a much smaller telescope, which is Spitzer. And in particular, one of these legacy program is GRATES, Goods Re-ionization Era Wide Area Treasury from Spitzer, led by Ivo Labbe, which is adding quite a lot of deep data over the Goods North and Goods South fields. To give you a rough idea, so we are reaching like 150 hours depth over approximately 150 square arc minutes across the two fields. You can have an idea of the improvement in depth in this figure here between the old good, the original good Spitzer imaging and what is offered by GRATES. So using this data, we can start probing the main stellar population properties of galaxies. And what I'm showing here is a stacked AD roughly corresponds to what we were able to do before adding GRATES. So we were able to probe only approximately, roughly, the galaxies brighter than L star or so. But thanks to GRATES, we can enormously dive deep into into much fainter galaxies. So we can go to about 1 magnitude and more fainter. And the analysis of the average properties of these galaxies, of redshift 8 galaxies, is revealing that their age on average, again, are very young, less than 50, 100 mega years. And this comes from both the analysis of the continuum and also by the very strong emission lines that we infer exist from the very red iron colors. We can also better formalize this picture by measuring the specific star formation rate. So the specific star formation rate is the ratio between the star formation rate and the stellar mass. And it has, dimensionally, it is the inverse of time. So it gives us an idea of the time scale of formation of stellar mass. So when we do this and compare the results that we obtain at redshift 8 to those at lower redshift, also similar redshift, as you can see here, we see that there was an evolution. But the most interesting part is that the evolution, at least at the redshift 4 and above, is consistent with the evolution of the specific dark matter accretion rate. So it's the equivalent of a specific star formation rate, but for dark matter halos. And this, which is represented by this solid line. And this solid line is derived from very straightforward algebra, let's say, on cosmology. So this is an indication, a first indication that the mass assembly followed the assembly of the dark matter halo. But we can also go a step further, or look at the problem from a different perspective, which is looking at the evolution of the stellar mass. So we can study the volume density of galaxies in bins of stellar mass, which is the stellar mass function, in the first billion year of cosmic time. And we did this using complementing the Grates data over the Goods fields with the other Canders fields. So we in total, we accumulated data over an area which is approximately 3 times larger than previous studies. And here I'm showing you the stellar mass function that we measured compared to previous estimates. We can study the evolution also of the stellar mass density. Here in this plot, I'm showing the evolution of the star formation rate density, which is obtained from very recent studies. And the interesting thing is that even also the evolution of the star formation rate density seems to follow, especially at very high redshift, as you can see, redshift 10 and 9 and 8, seems to follow the evolution of the dark matter halo accretion rate. So even in this case, the dark matter halo, the stellar mass seems to follow the evolution of the dark matter halo. But this is a punctual, it's a value which is fixed in time, but we can ask ourselves what happens if we integrate with time the star formation rate density. And this is exactly the stellar mass density, which is shown here. So the red points are our measurements of the stellar mass density that we obtained from the integration of our stellar mass function. And you can see that there is quite a drastic evolution, especially between redshift 8 and between redshift 10 and redshift 8. But again, another very interesting thing is that in the orange region here shows the evolution of the dark matter halo mass density. So it's, again, the equivalent of the stellar mass density, but applied to dark matter halos, which I have rescaled by a factor 100. It's constant across time. And you can see that there is no fit involved, apart from abundance matching, but we can discuss later. You can see that the evolution of the stellar mass densities follows quite well the evolution of the dark matter halo mass density. But these measurements of the stellar mass density are dominated by the values of the volume density at the low mass end. We can also ask ourselves what happens if we inspect the evolution at each values of stellar masses. And this is what I'm going to show here. So here you see the dark matter halos as a function of stellar mass. These are recovered through abundance matching. And this is for redshift 6. So we can do the same as redshift 7, redshift 8, redshift 9, and also redshift 10. And this quite surprising, I would say that we find no significant evolution in the stellar to halo mass ratio, so in the star formation efficiency between redshift 10 and redshift 6 of these galaxies. So this stellar mass function and results on the evolution of a star formation efficiency refer to sort of sub M-star galaxies, so galaxies which have a mass below the characteristic mass of the stellar mass function. So what happens with galaxies with much more massive galaxies? So in order to study this, we assemble a sample of 40 very bright star-forming galaxies at redshift between 6.5 and 9 or 9.5 across 7 square degrees of sky, which benefits from very deep optical, near-infrared, and IRAC data. And we follow up this with ALMA to study their ISM properties. And this is the result of the REBELS program, Re-ionization Era Bright Emission Line Survey, led by Richard. Here I'm showing you in a glance the results, because tomorrow, Sander, please, at this time, will show you in much more detail the results of REBELS. But we detect approximately 18 galaxies with very high confidence in C+ from ALMA, and approximately 30 if we relax a little bit the the requirements on the significance. But what the reason why I brought up this is that how can we improve on our knowledge of the star formation efficiency? So for this, leveraging the results from Rebels, we cannot use any more Spitzer, but we really need the power of JwSt. And actually, we've been lucky. I'm so super happy that one of our programs got accepted for observation with JwSt. So we are going to target 12 of the most robust spectroscopically confirmed bright galaxies from Rebels. So we have C+ already for this. And we are going to target this with IFU, low resolution prism observation. And these are going to give us a lot of information from UV slope, Lyman alpha. You can see some of the main science topic summarized in this figure below. Specific star formation rate from H alpha, stellar mass from access to line-free continuum, and also we can do this not just for the object as a whole, but also by looking at potential radial profile dependencies. Okay, so I think I'm up with my time. I'll leave here my conclusion and I'll take any question. Thank you.
Thank you, Mauro. Wait just a little bit while people type their questions.
In your SCD analysis, I see many bright lines are included in the broadband filter. Is comparing broadband photometry, including potential line emission to the model SCD, good enough to infer physical parameters, or do you need to separate line emission and continuum?
Yes, you need to separate line emission and continuum. But we did the stacking. So we picked Redshift 8 because it's a sort of nice niche for this kind of study, because the 4.5 micron data is contaminated by very strong O3 H beta and other minor lines. But the 3.6 micron data is relatively free from emission lines. There is O2, but it's not as strong as O3 and H beta. So the 3.6 already gives us a relatively robust measurements of the continuum. So we can also estimate the strength of the emission lines in the 4.5 band, and again recorrect the 3.6 micron band for O2 and get an even better estimate of the continuum, and so get also a better estimate of the stellar mass. This is not easy to do at a different redshift because, of course, as a different redshift, we have different emission lines entering and leaving the IRAC band. So one has to be careful about that. And I spent quite a lot of efforts in the stellar mass function because, of course, in that case I was probing from redshift 6 to redshift 10, and depending on the redshift and also on the significance of the IRAC detection, I was trying to correct to the best that I can, correct or estimate to the best that I can the contribution of different emission lines to the continuum.
All right, that's the only question that's popped up so far, but we're about out of time. So if you have more questions, please put them in the Slack, and then Mauro, you can check it out. Actually, one word popped up there, I'll let you respond to there. So thank you, Mauro. And our next talk is by Jana Kusanova. Jana, would you like to share your screen? And the title is The Host Galaxies of Radiolog Quasars at Redshift Greater than 6.
Yeah. So I hope you can see my screen.
Everything
is all right. Okay, great. So First of all, thank you very much for organizers for giving me this opportunity to give this talk. And today I'm going to talk about the recent results I obtained with NOEMA observations of the host galaxies of radio loud quasars at redshifts above 6. So this is exactly the redshifts where we observe the epoch of reionization. And at these redshifts in the recent decades, hundreds of quasars were discovered. And now we go as far as to redshift 7.5. But most of these quasars are radio quiet, and only 5 from the quasars at redshifts above 6 are radio loud. And the highest redshift of the radio loud quasars is currently 6.8. It was a recent discovery by Eduardo Bañeras. And compared to radio loud quasars, the host galaxies of radio quiet quasars were extensively observed with ALMA and with NOEMA. And we can observe the farthest frame infrared continuum. We can observe the C2 emission lines, and both of radio quiet quasars are detected. So they are in star-forming host galaxies, but little is known about the host galaxies of radio loud quasars and how the feedback from the jet is affecting the host galaxy. So in order to determine if it's quenching the star formation or it's enhancing the star formation, we need to observe these quasars. And recently we observed 4 quasars. One is missing. It is also a recent discovery. But 4 of them are observed with NOEMA. And these are the summary of the results of these observations. You can see the continuum images on the top panel and the C2 emission line images on the bottom, on the middle panel, and the spectral profile of C2 line emission at the bottom. So the interesting thing is that it seems that all these quasars, they are kind of in 2 completely different groups. There are 2 of them which are very faint, and in one of them we don't detect neither continuum emission nor C2 emission, and 2 of them are very bright. And even like in this one, in this quasar where we observe some C2 emission, this emission is still much fainter than for this 2 on the right panel. And the brightest ones, they look very similar. They have like almost the same continuum emission and almost the same C2 emission. But the question is like why these radio loud quasars are kind of like in these 2 groups with very faint and very bright. If like in some of them the feedback is suppressing star formation, or in other ones are enhancing star formation, or there's some other explanation. So if you look at the brightest quasars from the sample, they're not just the brightest in the observations of the C2 line emission and millimeter continuum emission. They are also the brightest in the X-ray, and they're also the most radio loud quasars from the sample. And one of them actually was like this one is a blazar, while the other one is not confirmed as a blazar, but it's outshining the blazar in the X-ray. So these 2 objects, they have extreme properties in the X-ray. They are the brightest at redshift above 6. And we know that in the radio quiet quasars, the C2 emission comes primarily from the photodissociation region, so it's linked to the star formation. But if in these 2 sources the C2 emission is coming from the X-ray dominated region, then this would explain the difference between the 2 groups. Maybe the C2 emission in these 2 brightest quasars is actually not related to the star formation, but related to the X-ray dominated region. And then without the radio jet we would observe, if we would subtract this part which is coming from the X radiominated regions, then we would also observe fainter C2 emission. I think I went to the different slide, sorry. So next, let's look at the spectral energy distribution. And here the radio observations are shown as squares, and the fit to the observation is shown as dotted lines with the power law. And the NOEMA results are the field stars, and the fit to the NOEMA observations with the modified black bunny model is shown as the solid lines. But the problem is, first of all, you can see that there is kind of correlation between the brightness of the fine thread continuum and the brightness at the radio wavelengths, because like all of the quasars, the high is the radio flux, the high is the flux in the far infrared. But if we extrapolate the power law from the radio observations, then we can see that at least in one object, the contribution from the synchrotron emission can be significant, and this is in this blazar. But in the other object, which is also the brightest object, if we extrapolate the contribution from radio emission, it's not as significant. But still, like for these two objects, we don't know exactly if this far infrared continuum flux is coming only from star formation and from the cold dust, or there is some additional contribution which is not taken into account, and then the star formation would also be lower and maybe closer to the fainter objects. So they look very similar, but in the same time, they might be, these two brightest objects might be different. And finally, I want to show the plot with star formation rate estimates based on the fine thread continuum measurement and based on the C2 line. And here also there's a difference between these two groups, because for the faintest ones, the results from fine thread and from the C2 emission, they are consistent with each other. But there is a big difference between the star formation rate based on the C2 emission and star formation rate based on the fine thread continuum for the brightest radio allowed quasars. And the problem here is that there is still some uncertainty, and because these measurements are based on the modified black body, and if the fine thread continuum flux does not only come from the star formation and from the cold dust in the galaxy, then these measurements can be slightly lower. But there are also some uncertainties due to the uncertainty on the dust temperature and on the emissivity index. So if we assume that all these measurements which are shown here are correct, and there are no other effects which are boosting the fine thread flux and C2 emission flux, then the radio allowed quasars would be very similar in their properties to radio required. But if it's not the case, then it's likely that they have lower star formation rates compared to radio quiet quasars. And finally, I want to show again this plot with a summary and point out to the spectral shapes of the C2 lines, because interestingly, two of them have some signs of a double Gaussian profile, and this could be explained as a merger. So the two of the radio allowed quasars can be hosted by galaxies with undergoing merger, and one of them has a single Gaussian profile, and it's not clear if it is a merger or not, because there are no high resolution observations. But it's also an interesting possibility that maybe the radio allowed quasars are hosted by mergers. So I'm going to leave you with the summary, and thank you very much for your attention.
Thank you very much, Jana. We'll wait a little bit while people type up their questions.
Okay.
Okay, in the SED plot, is the source with large synchrotron contribution a blazar?
Yes, yes, exactly.
And the second part of the question is, are your sources resolved by ALMA?
No, these sources which I show here, they were only observed with NOEMA. I don't have ALMA observations, but yeah, this is a possibility for the follow-up.
Next question is, for the SEDs, did you explore the effects of different dust temperature and emissivity indices on the FAR-IR-based SFR?
No, I haven't explored it, but this is in my plans to do it.
Okay, this is related to an earlier question. Are the sources resolved in the radio data?
Yes, and actually, like some of this, these sources which show some the signs of the mergers in the radio data, they also show two components. So it's quite likely that they are actually the mergers.
Okay. All we have so far, but we'll wait a little bit more, see if any other questions come in. Well, if any of you come up with more questions, we encourage you to put them in the Slack, and Jana can write back to you there. So thank you, Jana. We are a couple minutes ahead of schedule. So Ashwin, if you want to share your screen, but then we'll hold up a couple minutes before we get started so we don't get too far ahead.
Yeah.
Wait 2 minutes. All right, we can go ahead and get started. So the next talk will be by Ashwin Vijayan, talking about the properties of massive dusty galaxies at cosmic dawn.
Hi all, I am Ashwin Vijayan. I'm a final year PhD student at the University of Sussex, UK, working with Peter Thomas and Stephen Wilkins, studying the properties of galaxies in the epoch of reionization. In this talk, I will explore a few select dust-driven properties of massive galaxies that we observe in the FLARES suite of simulations. I would also like to bring attention to some of the people that I'm working with as well. Christopher Lovell, Peter Camps, Martin Bass, you see Kasisto, Will Roper, and the extended like Eagle and Skirt development teams. So probably this would be the last FLARES talk until we meet at another conference, I guess. So Will and Chris talked in quite a detail about the FLARES simulation. So I think I'll give an even briefer introduction. So we simulate a range of over-densities from a big dark matter only box. So our aim is to get some of these massive galaxies in the epoch of reionization. We re-simulate them with the very successful Eagle simulation physics, which was tested, and it produced really good match to the observations that in the local universe. So our aim is to test the Eagle physics at the higher redshift, namely the epoch of reionization. So I'll give like a small primer to some of the properties that I'll be discussing here, namely two. So when studying the high C galaxies, the infrared excess UV continuum slope or the IRX beta slope is a relation that is widely used. So this is used to usually estimate the attenuated or the obscured properties from the UV observation of galaxies. One such relation that was calibrated in the low Z universe was the starburst relation found in for the starburst galaxies found in Muir et al. 1999. So they show like a really tight relation when you plot the IRX against the beta, and this has been used to to get the dust obscured fraction in many of these higher redshift studies. Another one is the dust SCD temperature. This is used usually in modified black body fits to obtain the infrared luminosity and then get the infrared excess. So for example, recent work show an increasing value towards high C. So you can see on the right a plot from Bouwens et al. 2020 paper, which shows an increasing dust temperature, which is and a fit was obtained for observations found across redshifts. So I'll move on to give an introduction to some the galaxy sample we are using. So we only use some of the massive galaxies that we have in the simulation, basically anything greater than 1,000 star particles approximately. It corresponds to around 10⁹ in solar mass. We have a peak star formation rate closer to 1,000 solar mass per year. This can be seen in this plot I have shown on the right, which is plotting the stellar mass against the star formation rate. And you can see that we have a really good statistical sample of massive high C galaxies. And with this, we hope to study some of the dust-driven properties. So how do we generate the SCDs? So we use the publicly available radiative transfer code, SCRT, to produce the full SCDs. So we use a prescription which is quite similar to what was done in CAMS 2016 and TRAFOR 2017 with some modifications. Similar to that, we model young stars and birth clouds using the mappings 3 templates and old stars using BPAS. We fixed the DTM ratio for different galaxies from this fitting function we obtained from previous work we did with the L galaxy simulation, the semi-analytical model, trying to model the evolution of dust in galaxies. We also use an SMC type of dust distribution, which is supposed to be applicable to high C galaxies. We do not take into account AGN emission on the SEDs, and we do not calibrate to any of the observations. On the right, I have shown a sample SED from a galaxy at redshift 8 with approximately 10 raised to 11 solar luminosity in the infrared. We also had a different model that we presented in the previous paper, which uses a line of sight dust extinction model, and it is quite flexible and much faster than running a full radiative transfer simulation, not a simulation, sorry, post-processing the galaxies with a full radiative transfer code. So before moving on to the properties that I'm going to explain, I'll briefly look at the high C luminosity functions. The first one is the UV luminosity function. So you can see on the right, I show the luminosity function from Z equal to 5 to 10. We are incomplete at the faint end due to the selection of the most massive galaxies. We do provide a reasonable match to the extreme UV number densities. And here is the infrared luminosity function. This one is also incomplete at the faint end because of the selection. It agrees reasonably well with some observations in different regimes. As you can see, there are also some inconsistencies with some of the observations at different redshifts. But one thing that is quite clear if you look at redshift 5 is that we severely underpredict the number density of extreme infrared luminous source at Z equal to 5. And this is one of the places where, so if you look at this region where two different sets of observations agree with each other and we fail to match up to that. So what are the reasons for this? So this has been studied in other Eagle simulation papers where they show that the SFR function is predicted to be a bit lower in the Eagle galaxies. This was explored in the Katsianis 2017 paper. And we also explored in flares in level 2021, where if you look closely, there is some slight underprediction. And to the to people who have paid close attention to the UV luminosity function, you can see that this is almost similar to that small underprediction we had for the UV LF. Another reason was like a lack of bursty star formation, which was shown in BAS 2020 when it was trying to understand why the infrared luminosity function was unpredicted in the local universe. So another possible reason could be a transition to top-heavy IMF in some of these extreme galaxies. So simulations like SIMBA have shown that you can get better agreement with the sub-millimeter counts. See Chris's paper in 2021, which is due to the higher SFRs compared to the Eagle simulation in SIMBA. But there are also caveats, like you can get this lack of quiescent galaxies as shown in this plot on the right. So what we need is like a fine interplay of feedback and star formation recipes at higher redshift. Maybe maybe we could look for some calibrations at higher redshift as well. After that small detour and explaining some of the caveats in the model that we are using, I'll talk about the IRX beta relation now. On the right, I've plotted the IRX beta relation along with some of the observations for redshift 5 to 10. As you can see, the relation from flares follows a local starburst relation, and it is quite well matched to many of the observations that you have at these higher redshifts with a few low mass galaxies following the SMC-like curve. There's also a few deviations. There are also a few galaxies in the observation that show these low IRX, high beta, but we fail to predict some of these galaxies. We are not sure what the exact reason is. There are other models that have shown the same thing. For example, the FIRE2 simulations produced quite similar results with showing a lack of low IRX, high beta galaxies. I'll look at the dust temperatures. Now, we namely look at the luminosity weighted dust temperature, which is one of them is the peak dust temperature or the peak wavelength at which the infrared emission peaks. We also look at the mid-infrared power law plus the modified black body fit that gives you an SED dust temperature, and also an optically thin modified black body dust temperature, which is used in many of the high Z studies to get the infrared luminosity. So as expected, you can see that the peak temperature is much lower compared to the other ones, and the optically thin one lies somewhere in the middle. So we predict for the peak dust temperature, we predict a relation which has a higher slope than compared to lower redshift relations like the ones which was shown by Liang et al. 2020 from the massive fire simulation, as well as the local redshift relation found in Schreiber et al. 2017, I think. And we see that the massive galaxies here follow a relation which is which has a much higher slope. We also failed to predict some of these really cold galaxies, cold dusty galaxies as well. Yeah. So here is the prediction for the dust SED temperature. So if you look at the optically thin dust SED temperature median relation, you can see that it is slightly above the Bouwens et al. 2020 relation that I showed earlier, which is also plotted here as this line. So what could it imply? It could mean that there might be the infrared luminosities predicted might be underestimated in some cases. There's also a similar case of this very low dust temperatures being seen in observations, but we failed to pick up some of these in our simulation results. So with that, I conclude my talk, and I probably would you probably could see this on arXiv soon. And we have quite a lot of work going on as well, like testing for bias and cosmic variance, effective AGN, prediction for Euclid and Roman dust continuum sizes, looking at the Balmer break. We also hope that we can do some prediction of the infrared properties from the UV. As Will explained before, FLAIRS 2 is already in development, and we are welcome to any ideas and collaborations. Thanks.
All right, thank you. Get to questions.
Okay, how much is this under prediction of IR luminosity due to missing AGN contribution to your simulated SEDs?
So I have a plot for that. Okay, so here's a plot of that. You can actually see there isn't much of a deviation that is being caused at these. Oh, sorry, I must explain before. So what we did here was we tried to add we calculated the bolometric luminosity that could be obtained from the supermassive black hole at the center, and then added it completely to the infrared luminosity to see how much of a leeway we can have. And we see that there isn't much of an increase in the infrared luminosity function as compared to the stellar only contribution. So the observations lie somewhere around here, and we still don't match up to the number densities.
Somebody would like to hear more details about your dust model.
So the dust model is based and everything is done in the skirt radiative transfer code. The only thing we add is the what should be the dust to metal ratio in the galaxies. Other than that, like choosing grain distribution type is done within skirt, so we do something like SMC. So if you want more specific answers, you could contact me.
All right, sounds good. We probably need to move on. There's more questions in the Slack. You want to check them out there. And we'll get to our last speaker for the day. This is Takahiro Yoshioka. He's going to be talking about mapping the spatially inhomogeneous cosmic reionization with Subaru hypersphere prime cam.
Can you see my screen?
Yes.
All right. Thank you for introduction. Hi, everyone. My name is Takehiro Yoshioka. I'm a graduate student at University of Tokyo. Today, I'd like to talk about mapping the spatially inhomogeneous cosmic reionization with Subaru HSC. One of the important features of cosmic reionization is its spatially inhomogeneous nature. Reionization of neutral hydrogen proceeded gradually from the surrounding of the newly formed objects, and then H2 regions formed the bubble-like structure as shown in the right picture. This reionization topology is determined by several parameters such as the distribution of ionizing sources, ionizing photon escape fraction, and the density of our intergalactic medium. So investigation of reionization topology is important for studying these parameters. Lyman-Fab fraction is one of the widely used methods to investigate reionization. The Lyman-Fab fraction is defined as the fraction of Lyman-Blake galaxies that show Lyman-Fab emission lines. Right figure shows the Lyman-Fab fraction as a function of redshift. The Lyman-Fab fraction increases from redshift 4 to 6, partly due to the less dust content of high redshift galaxies. On the other hand, Lyman-Fab fraction decreases rapidly at above redshift 6. This sharp drop is thought to be a signature of reionization. Although the Lyman-Fab fraction is a good probe of reionization, the Lyman-Fab fraction measurements in the previous studies require spectroscopic observations. As a result, it is much difficult to obtain large sample sizes. Therefore, those studies can only determine the average neutral fraction of the universe, and they cannot investigate the spatially inhomogeneous reionization. To overcome this problem, we use Subaru hypersphere cam HSC. HSC has a very wide field of view, enough to detect inhomogeneous reionization, as shown in the right figure. From this wide field observations with HSC, we can efficiently detect LAEs and LBGs. Taking advantage of this unique feature of HSC, we aim to observe for the first time spatially inhomogeneous reionization by efficient survey of LAEs and LBGs at redshift 6.6. Then we describe our observations and samples, galaxy samples we use. We use imaging data on the 1.5 square degrees UD cosmos field taken by HSC SSB. We detect LAEs at redshift 6.6 on the flux excess based on the flux excess in narrowband filter as shown in this color magnitude diagram. And we obtain 189 LAEs. Then we detect LBGs at redshift 6.6 by using the Lyman-Blake technique as shown in this two-color diagram. And we obtain 179 LBGs. One important thing here is that we have to detect LAEs and LBGs at the same redshift to probe reionization. For this purpose, we use the newly installed intermediate band filter IB945. The filter transmission curve is shown in the top right figure. IB945 makes it possible to detect LAEs and LBGs simultaneously at the same redshift, 6.6. The selection functions of our samples are shown in the bottom right figure. Though the width of LBG selection function is wider than that of LAEs, it is much narrower than that of typical Z dropout sections. From the selection function, we find that using the using IB945 can achieve selecting LBGs at almost the same redshift as LAEs. As we select LAEs and LBGs separately, the redshift range and limiting magnitude of them are not the same. But to correct these differences, we apply these selection functions and limiting magnitudes to a simulation model when we calculate the neutral fraction. Please note that our methodology is a bit different from the typical line of fraction with spectroscopic observations. Using the selection criteria described in the previous slide, we calculate the selection completeness of LAEs and LBGs by molecular simulations. After the completeness correction, we find that the surface densities of our sample are consistent with previous studies. Here we calculate the density distributions of LAEs and LBGs. The black dots indicate the position of the LAEs and LBGs, and the background color maps indicate the overdensity. Next, we estimate the neutral fraction of the universe from the observed LAE to LBG number ratio. After the completeness correction, the LAE to LBG number ratio is found to be 0.76 plus minus 0.1. Here we use a simulation model of Inoue et al. To estimate the neutral fraction. In the simulation model, they find a correlation between number ratio and neutral fraction, as shown in this figure. This simulation model is a combination of large-scale n-body simulation and radiative hydrodynamic simulation, and it computes dark matter density, ionizing photoradiative transfer through the IDM, and galaxy formation. By using this relationship, the average neutral fraction in the field of view is estimated to be less than 0.4 from the observed number ratio. Now our results are consistent with the previous studies. Next, we show the spatial distribution of LA to LBG number ratio. In the field of view, the variation of number ratio is a factor of 3. And this difference may reflect the spatially inhomogeneity of cosmic reionization. It implies that the reionization is in progress where LA density is high. On the other hand, reionization is delayed where LA density is low. But this variation may be due to the intrinsic distribution of galaxies. So we will discuss it later in our talk. The scatter spatial variation of LA to LBG number ratio is shown in this red marks. However, as seen in this figure, the uncertainty of the number ratio is large due to the shallow depths of our observation. So we cannot give a strict constraint on the neutral fraction. Unfortunately, we cannot detect the spatially inhomogeneous reionization. Then we discuss one problem that must be considered to detect the spatially inhomogeneity of reionization. Because the number of galaxies also depends on the large-scale structure, the variation in the number ratio may be due to the intrinsic large-scale structure without IgM absorption. The right figure shows the scatter of number ratio with IgM absorption as a function of aperture size within which we calculate the number ratio. In this figure, we find that the scatter of LA to LBG ratio is large in the smaller aperture size. So we find that a large aperture size is necessary for this aim. To distinguish a reionization topology from the large-scale structure, we compare the scatter of number ratio with and without IgM absorption in the simulation data. And we find that the scatter with IgM absorption is slightly larger than that without IgM. We think this difference is aroused from the reionization topology. However, this difference is not significant, so we find that it is hard to distinguish them, even with much deeper observations than our current survey. Finally, we calculate the Lyme alpha equivalent width and compare the equivalent width distribution between high and low, between LAs in high LA density regions, shown in blue, and LAs in low LA density regions, shown in orange. We find that LAs in high LA density regions more populate higher equivalent widths. From this figure, low LA density region implies higher neutral fraction, while the statistical significance is not sufficient. In summary, we attempted to investigate for the first time the spatially inhomogeneous reionization from the efficient survey with SWAL HSC. We found that mapping the spatially inhomogeneous reionization requires much deeper imaging, and that it is difficult to distinguish the reionization topology from the large-scale structure. That's all. Thank you.
Thank you, Takahiro. We'll wait just a minute to see if we get any questions.
Okay, have you measured a two-point correlation function of LAEs and LBGs?
Not, I haven't measured it, but I think it's interesting.
I'll just ask, can you say any more about how the model you use sort of populates the intrinsic Lyman alpha luminosity of galaxies?
Okay. About the reionization simulation, we use a combination of hydrodynamic simulation and n-body simulation. In the simulation model, they use a typical model for simulate Lyme alpha emission lines. The Lyme alpha emission line is determined by the halo mass. Lyme alpha luminosity is correlate with halo mass as shown in this figure. And from this simulation reproduces the Lyme alpha luminosity function, autocorrelation function, and LA fraction of the observations in the literature.
So do you plan to observe other extragalactic fields with the IB 945 filter?
No, we don't plan to other fields with IB 945.
All right, that's there's one more question. We'll do one more. So it looked like you had a region at the top center which was overdense in LBGs yet had few LEEs. Does this still fit into the reionization picture, or is this consistent with scatter?
Here, about this figure. overdense in LBGs. Top center here. I don't find any inconsistency with reionization picture, but I think it's interesting the LA dense distribution and LB distribution is different at almost the same redshift. That's clear. I don't know if that's a clear answer for the question.
We'll let the questioner follow up in the Slack if they like.
Okay.
Thank you very much for your talk, Takahiro. And thank you to all the speakers in sessions 4A and 4B and 3A and 3B while we're at it today. Today was a long day. So we hope that you will join us tomorrow at 13:30 UTC for the final 2 sessions of SAZERAC. We will see you all then. Have a good rest of your day.